This is the Discord blog from discord.com. How Discord stores billions of messages. This is from 2017, but still interesting, of course. Discord continues to grow faster than expected, and so does our user-generated content. With more users comes more chat messages. In July, we announced 40 million messages a day. In December, we announced 100 million a day. And as of this blog post, we are well past 120 million. We decided early on to store all chat history forever, so users can come back anytime and have their data available on any device. This is a lot of data that is ever increasing in velocity, size, and must remain available. How do we do it, Cassandra? I'm sure they have also challenges with Cassandra. Nothing is smooth, right? What we were doing, the original version of Discord was built in just under 2 months in early 2015. Arguably, one of the best databases for iterating quickly is MongoDB. Everything on Discord was stored in a single MongoDB replica set, and this was intentional, but we also planned everything for ease migration to a new database. We knew we were not going to use MongoDB sharding because it is complicated to use and not known for stability. So they started with MongoDB. They planned it already for a case where they need to migrate, so probably the APIs are the same, and they didn't want to use the sharding, at least back then, because it was complicated. And so they say they potentially saw issues with stability. This is actually part of our company culture. Build quickly to prove out a product feature, but always with a path to a more robust solution. Really like this. Always have a path for a more robust solution, but start building quickly. Perfect. The messages were stored in a MongoDB collection with a single compound index on channel ID and created that. So the index was a compound ID of channel ID and created that. Created that is a datetime that the message was sent or created, and channel ID is the channel ID in Discord. It's chats. Around November 15, 2015 reached 100 million stored messages, and at this time we started to see the expected issues appearing. The data in the index could no longer fit RAM and latency. So you see, with MongoDB, the data and indexing, so maybe the indexing for sure, the data not sure. All of this needed to be in RAM, probably because of using B-trees. MongoDB uses B-trees for indexes. Believe it or not, NoSQL still need to use B-trees, I think. And B plus trees might ease the solution. So the latencies started to become unpredictable. It was time to migrate to a database more suited to the task. I wonder what would happen if they would just change from, open the open source, if it's an open source MongoDB, and change it to B plus 3. Choosing the right database. Before choosing a new database, we had to understand our read-write patterns and why we were having problems with our current solution. It quickly became clear that our reads were extremely random. Random meaning which message you read. Do you read latest message? Do you read the message, do you read the message a week ago? And our read-write ratio was about 50-50. Voice chat heavy Discord servers send almost no messages. Yeah, so Discord supports also voice chat. Over there they didn't have much messages. This means they send a message or two every few days. In a year, this kind of server is unlikely to reach 1000 messages. The problem is that even though this is a small amount of messages, it makes it harder to serve this data to the users. Just returning 50 messages to the users can result in many random 6 on disk, causing disk caches eviction, because it's from a long time ago and we said that they use the channel ID and the date. Private text chat heavy Discord servers send a decent number of messages, easily reaching between 100,000 to 1 million messages a year. The data they are requesting is usually very recent only. The problem is since these servers usually have under 100 members, the rate at which this data is requested is low and are likely to be in this cache. So we are still describing the issues with the original design. Large public Discord servers send a lot of messages. I mean the state, so they can choose database. They have thousands of members sending thousands of messages a day and easily rack up millions of messages per year. They almost always are requesting messages sent in the last hour and are requesting them often. But because of that, this data is usually in the disk cache. So really a lot of scenarios. Some are voice messages with no messages, some are chat channels with messages, some are chat channels on this cache. We knew that in the coming year we would add even more ways for users to issue random reads, the ability to view your mention for the last 30 days, then jump to that point in history, viewing plus jumping to pinned messages, and the full text search. They were introducing new features, so they need to support not only viewing the latest message, but also previous ones, and also search. All of these spells more random reads. Next, we defined our requirements. So linear scalability, we do not want to consider the solution later. Automatic failover, we love sleeping at night. Low maintenance, it should just work. Proven to work, we love trying new technology but not too new. Predictable performance, we have alerts go off when our API's 95 percentile goes above 80 milliseconds. We also do not want to cache the messages in Redis or Memcached. So rather than caching on Redis or Memcached, we are okay with 95 percentile 80 milliseconds. This would simplify the design because we would have a single database without a cache, without another database for cache. Not a blob store. Writing thousands of messages per second would not work great if we had to constantly deserialize blobs and append them. Open source, we believe in controlling our own destiny and don't want to depend third-party companies. Cassandra was the only database that fulfilled all our requirements, at least back then in 2017. You can just add nodes to scale it and it can tolerate a loss of nodes without any impact on the application. Large companies such as Netflix and Apple have thousands of Cassandra nodes. Related data is stored continuously on disk, providing minimum 6 and easy distribution around the cluster. It's backed by DataStax, but still open source and community driven. Having made the choice, we needed to prove that it would actually work. Data modeling. The best way to describe Cassandra to a newcomer is that it's a KKV store. The two keys comprise the primary key. The first key is the partition key and used to determine which node. So the first key is in order to find which node to go to, the data lives on, and it is found on disk. The partition contains multiple rows within it, and the row within a partition is identified by the second key, which is the clustering key. The clustering key accesses both primary key within the partition and how the rows are sorted. You can think of the partition as an ordered dictionary. These properties combine to allow very powerful data modeling. Remember that messages were indexed in the MongoDB using channel ID and created that. Channel ID became the partition key, since all queries operate on a channel. Yeah. But created at didn't make a great clustering key. They need now to think, what secondary key do we want? Because two messages can have the same creation time. So this would not uniquely identify messages. Luckily, every ID on this code is actually a snowflake chronologically sortable. So the IDs themselves of the messages are chronologically sortable. This can be done with a combination when you concatenate a UUID and a timestamp, or a timestamp and UUID, so you can sort them. So we were able to use them instead. The primary key became channel ID, message ID, where the message ID is a snowflake, a chronologically sortable ID. This meant that when loading the channel, we could tell Cassandra exactly where to range scan for messages. Here's a simplified schema for our message table. This omits about 10 columns. The important thing here, primary key, channel ID, and message ID, and we said that message ID is chronologically sortable. While Cassandra has schemas not unlike relational databases, they are cheap to alter and do not impose any temporary performance impact. We get the best of a blob store and a relational store. When we started, I wonder what they said today about Cassandra. I mean, it's been 6 years since then. When we started importing existing messages into Cassandra, we immediately began to see warnings in the logs telling us partitions were found over 100 megabyte size. What gives Cassandra advertises that it can support 2 gigabyte partitions. Apparently, just because it can be done, it doesn't mean it should. Large partitions put a lot of GC pressure, GC Java pressure on Cassandra during compaction, cluster expansion, and more. Having large partitions also means the data in it cannot be distributed around the cluster. It became clear we had to somehow bound the size of the partitions because a single Discord channel can exist for years and perpetually grow in size. We decided to bucket our messages by time. We looked at the largest channels on Discord and determined if we stored about 10 days of messages within a bucket, we would comfortably stay within so they wanted to limit the number of data in partition, so they reduced it to 100 megabytes. They looked at the number of days and reached the conclusion need 10 days in a bucket. Bucket had to be derivable from the message ID or timestamp. Make bucket. If Snowflake is num timestamp, Discord epoch, and then they divide the timestamp by the bucket size in order to get a bucket size. Cassandra partition keys can be compounded, so our new primary key became channel ID and bucket and then message ID. Aha. So now when we decide what is the partition, it's both the channel ID bucket and then also message ID. So primary ID, channel ID bucket, and message ID. So to store the partitions less than 100 megabyte. To query for recent messages in the channel, we generate a bucket range from the current time to channel ID. It's also Snowflake and has to be older than the first message. We then sequentially query partitions until enough messages are collected. The downside of this method is that it's rarely active Discords will have to query multiple buckets to collect enough messages over time. Yeah, because the bucketing is over time. So you would have multiple buckets, some buckets will be in older time. In practice, this has proved to be fine because for active Discords, enough messages are usually found in the first partition and they are the majority. Importing messages into Cassandra went without a hitch and we were ready to try it in production. Dark Lunch. Good practice, Dark Lunch. Introducing a new system into production is always scary, so it's a good idea to try to test it without impacting users. We set up our code to double read. So when they read also from old database, from new database, and then the double write, write to old database to new database, to MongoDB in Cassandra. Immediately after launching, we started getting errors in our backtracker telling us that auto ID was null. How can it be null? It's a required field. Eventual consistency. Or as some calls it, no consistency in the beginning, only later consistency. Cassandra is an AEP, availability partition tolerance database, which means it trades strong consistency for availability, which is something we wanted. It is an anti-pattern to read before write. Reads are more expensive in Cassandra, and therefore everything that Cassandra does is essentially an upsert, even if you provide only certain columns. You can only write to any node, and it will resolve conflict automatically using last write wins. Semantics on a per column. So how did this bite us? In the scenario that the user edits a message at the same time as another user deletes the same message, we ended up with a row that was missing all the data except the primary key and the text, since all Cassandra writes are upserts. There were two possible solutions for handling this problem. One, write the whole message back when editing the message. This had the possibility of resurrecting messages that were deleted and adding more chances for conflict for concurrent writes. 2. Figuring out that the message is corrupt and deleting it from database. We went with the second option, which we did by choosing column that was required, in this case author-ID, and deleting the messages if it was null. While solving this problem, we noticed we were being very inefficient with our writes. Since Cassandra is eventually consistent, it cannot just delete data immediately. It has to replicate delete to other nodes, and do it even if other nodes are temporarily unavailable. Cassandra does this by treating deletes as a form of write calling called a tombstone. On read, it just skips over tombstones that comes across, but what happens if you have too many tombstones, and then most of what you do is skip the deletes. Tombstones live for a configurable amount of time, 10 days by default, and are permanently deleted during compaction when that time expires. Deleting a column and writing null to a column are the exact same thing. They both generate a tombstone. Since all writes in Cassandra are upserts, that means that you are generating a tombstone even when writing null for the first time. In practice, our entire messages schema contains 16 columns, but the average message only has 4 value set. We're writing 12 tombstone into Cassandra most of the time for no reason. The solution was to simply only write non-null values to Cassandra. Not that clear actually. Deleting and writing null to a column are the exact same thing. It was simple, only write non-null. Okay, so they say maybe some of the fields were null because they are not often used, so they were also tombstones. So they stopped writing them. Interesting. Performance. Cassandra is known to have faster writes than reads, and we observed that exactly. Writes were sub-millisecond and reads were under 5 milliseconds. We observed this regardless of what data was being accessed. This is important to know about Cassandra. It is better on writes. You see, writes takes sub-milliseconds and reads 5 milliseconds. Up to 5 milliseconds, probably because it needs to configure with multiple nodes the reads. And performance stayed consistent during a week of testing. Nothing was surprising, just got exactly what we expected. We see here the latency of write, which is 0.5 milliseconds, and the latency of read, which is about 2.5 milliseconds. In line with fast, consistent, and performance, here's an example of a jump to a message from over a year ago in a channel with millions of messages, so it's pretty quick. The big surprise. Everything went smoothly, so we rolled it as our primary database and phased out MongoDB within a week. It continued to work flawlessly for about 6 months until that one day where Cassandra became unresponsive. We noticed Cassandra was running 10 seconds stop the world GC constantly, but we had no idea why. We started digging and found a Discord channel that was taking 20 seconds to load. The Puzzles and Dragons subreddit public Discord server was the culprit. Since it was public, we joined it to take a look. To our surprise, the channel had only one message in it. One message it had. It was at that moment that it became obvious they deleted millions of messages and now they need to scan tombstones all day, leaving only one message in the channel. If you have been paying attention, you might remember how Cassandra handles deletes using tombstones, measured in eventual consistency. When a user loaded this channel, even though there was only one message, Cassandra had to effectively scan millions of messages tombstones, generating garbage faster than the JVM could collect it. We solved this by doing the following. We lowered the lifespan of tombstone from 10 days down to 2 days. After 2 days, it would even delete completely data, no tombstone left. Because we run Cassandra repairs and anti-entropy process every night on our message cluster. But how does this help the DNSA? We changed our query code to track empty buckets and to avoid them in the future for a channel. This meant that if a user calls this query again, at most Cassandra would be scanning only in the most recent bucket, the future. We are currently running a 12-node cluster with a replica factor of 3. Each data point is written to 3 replicas and will just continue to add new Cassandra nodes as needed. We believe this will continue to work for a long time, but as this code continues to grow, there is a distant future where we are storing billions of messages per day. Netflix and Apple run clusters of hundreds of nodes, so we know we can punt. This is important. Netflix, Apple, and Discord are using Cassandra to write all the data. So we know we can punt thinking too much about this for a while. However, we like to have some ideas in our pocket for the future. Near term. What will happen in future with higher scale? Upgrade our message cluster from Cassandra 2 to Cassandra 3. Cassandra 3 has a new storage format that can reduce storage size by more than 50%. Newer versions of Cassandra are better at handling more data on a single node. We currently store nearly 1 terabyte of compressed data on each node. We believe we can safely reduce the number of nodes in the cluster by bumping this to 2 terabyte. It would also be interesting to know how they back up the data. What happens in case? Is Cassandra the final destination of the messages, or is it going to be some blob store? Maybe Cassandra. Long term, explore using Scylla, a Cassandra-compatible database written in C++. So not Java, we will not have the GC. During normal operations, our Cassandra nodes are actually not using too much CPU. However, at non-peak hours, we can run repairs. An anti-entropy process. They become fairly CPU bound, and the duration increases with the amount of data written since the last repair. Scylla advertises significantly lower repair times. Build a system to archive unused channels to flat files on Google Cloud Storage and load them back on demand. We wanted to avoid doing this one and don't think we will have to do it. Conclusion. It has now been just over a year since we made the switch, and despite the big surprise, it has been smooth sailing. We went from over 100 million total messages to more than 120 million messages a day, with performance and stability staying consistent. Due to the success of this project, we have since moved the rest of our live production data to Cassandra, and that has also been a success. In a follow-up to this post, we will explore how we make billions of messages searchable. Don't have dedicated DevOps engineers yet, only 4 backends, so having a system we don't have to worry about has been great. We're hiring. Yeah, this was a great one. He is both the CTO and co-founder. Looks good. So this was how Cassandra in 2017 moved from MongoDB to Cassandra to store a lot of data, and some challenges that they had, a dark launch, and how they overcame it, the partition key, everything. This was really a good one.